Good afternoon. My name is José Cepeda, and first of all, I would like to thank ADPC for the invitation to participate in this regional meeting. I would like to thank you also for your attention in attending this regional meeting. The topic I'm going to talk about here is about landslide flow path analysis and risk mapping. I work at the Norwegian Geotechnical Institute in the division for risk, landslides, and climate change. The presentation is going to be split in three parts. First, some basic concepts, then landslide flow path analysis, and finally, landslide risk mapping. The first basic concept we have to discuss is about risk. In short, is defined as the probability of losses, and mathematically, it can be presented as the product of hazard times vulnerability times the amount of elements at risk. Then each one of these components of the definition of risk we can explore in more detail, and we'll come back to this in a moment in each one of these details. Hazard and risk require also the definition of the concept of exposure. We can illustrate this with this example. Here we have two different layers of the same area. First, we have the elements at risk, which is composed by the building footprint in a populated area, and then the hazard footprint for the same area, which is given, for example, by the area affected by a potential flood or landslide. When we overlay both the building footprint, the hazard footprint, then we obtain from that overlay the information about which buildings are exposed, those that are shown in red here, and which are not exposed, shown in green. Therefore, we of course see that it's necessary to use GIS tools to come up with an appropriate appropriate framework for the analysis. As a simple example, using the previous slide, we can calculate the risk. In this case, we are given the information that the hazard event has a return period of 100 years. The buildings in the hazard footprint would be affected by having 10% of damage, and the cost of each building is 100,000 euro. And from the previous slide, we can see how many buildings would be affected by this hazardous event. So the calculation of risk would simply start by evaluating the hazard as an annual probability, and that is obtained by dividing by the inverse of the return period, so that would be 0.01, and then we multiply that by the consequences, and that will be given by 10% of the total cost of each building, and then we have to multiply by the number of buildings exposed, the number of exposed buildings, which are all the red buildings in this figure, and then at the end we'll get the risk in euros per year. Just for illustration, these are some steps that one has to follow when we have different types of hazards affecting an area. In this case, we're going to deal only in these examples with a single type of hazard, which is a landslide. The question of risk, we can remember it again like this. You can go through all these concepts in the presentations that you will be provided in due time by the organizers of the workshop. This is an example on how a calculation of specific risk is performed for a case of flooding. Here we have a single an event with a 10-year return period that is affecting this section of a river, or this section in an area nearby a river. This is the river. So when the flooding occurs, then due to the differences in the terrain, in the cross section, different buildings will be affected by different flood depths. This building will be affected by a flood depth of 4.5 meters, this one 5.6, and this one 0.8 meters. Then in this column we see the temporal probability of for the hazard for each building, which is just the one divided by the return period, so that will be 0.1. Then the economic value of each building is given here. Well, it's given here, and that's is the summation of the economic value of the buildings themselves and of the contents. And finally, the most important thing here is to figure out how much damage each building will suffer when exposed to this flood depth, or when affected by this flood depth. So this horizontal axis is basically giving us, or is presenting a hazard intensity parameter, which in the case of flooding is well represented by flood depth. And in the vertical axis, we have the percentage of damage for different type of constructions. For example, here we have two types of construction, type 1 and type 2. And these curves are vulnerability curves or fragility curves. The steepest these curves become, then that means that the structures are less resistant. So that means that with a lower hazard intensity, the structure is basically affected with a higher degree of damage. And the gentler these curves are, then that means that the structures are relatively stronger. So in this case, you see that type 2 of structure in general has a better resistance than type 1, because you see that for example for 6 meter of flood depth, the type 1 structure is completely destroyed, while for a 6 meter flood depth, type 2 has about 60% of damage. Then the vulnerability comes just by looking at the degree of damage for each type of structure that we read directly by taking the hazard intensity from the horizontal axis. Then we read on the corresponding curve. For example, for structure C, we have 4.5 meters. Structure C is of type 2, and then we read the degree of damage, which is 0.5. And then by making the product of all these columns, we come to specific risk, which in total gives us 16,000 monetary units, which we can assume are euros, for example. This is just for one single return period, but the same can be done for several return periods. Another way of looking at risk is by combining probabilities of occurrence versus potential loss. So, and this is generally presented in a format of a risk matrix. So the lower the probability and the lower the potential loss, then the lower the risk, which is shown in green here. And the higher the probability, which is shown here, when we go in this level, and the higher the potential loss, then we get a very high risk, and so on. This is an expanded example of the previous flood illustration of risk calculation with flood, but in this case, the exercise is performed for several return periods. So we have a flood with a 2-year return period, 10-year, and 50-year return period. So when we perform the calculation for each one of these events, we obtain a point on the risk, on the probability versus consequences space. And when we join these points, then we obtain a risk curve. A similar exercise can be done when, if we take as a landslide event in an area, or a landslide risk evaluation in an area. In this case, for example, the different scenarios for landslide hazard are given by different groundwater levels. So the deepest groundwater level, which is the let's say the event that has the shortest return period, and then as the groundwater level becomes shallower, then that means that you have higher probability for instabilities. Then we have the event with the longest return periods. And then the analysis performed in the same way as we did for the risk evaluation or for the flood analysis. In this case, for landslides, one has to keep in mind that the exposed area can be located both at the release area, like in the case of structure A, and also the exposed area can be located at the runout zone, like in the case of structures B and C. Here are some definitions from related to landslide risk from the Technical Committee 32 of the International Society of Soil Mechanics and Geotechnical Engineering. So it's more or less a convention that has also been agreed with the International Association for Engineering Geologists and also for rock mechanics. So it's more or less an agreed convention between geoscientists and engineers. Then we just have to maybe review what a landslide is. I mean, this meeting is basically all dealing about landslide risk management, but let's just take this like a short review, and we'll see why this is important. Well, landslide, we know it's the movement of a mass of rock, debris, or earth downslope, and the materials we can have can be rock or soil, and soil can be classified as earth when we have mostly finer particles, or debris when we have coarser particles. Regarding the types of movement, we can have falls, topples, slides, flows, and spread. And when we combine the naming and classification conventions that we are using are based on this joint technical committee, which is basically a joint committee between the societies of geotechnical engineers, engineering geologists, and rock mechanics. Then, based on that convention, landslides are in the most simple form, classified based on the type of movement and the material. So when we combine type of movement and material, we get the basic types of landslides. For example, rock fall, rock topples, rock slides, debris flow, and so on. Why is it important to keep in mind these different types of landslides? The most important reason is not really a scientific one, but it's a practical one, because each type of landslide will have a different physical behavior, and then this physical behavior leads to the fact that we have to analyze these different type of landslides with different approaches for analysis, and most important of all, the type of mitigation measures that each type of landslide requires, it also varies. So a mitigation measure that can be good enough for rock falls may not be good enough for debris flows, for example. So it's important to know which type of events we have at the initiation phase and at the runout phase. Main parts of a landslide, the initiation area, and then the runout zone. In this case, you see the runout zone is relatively small compared to the release area. So when we think of landslides, we have to think that we have to ask ourselves which phase or part of a landslide we're analyzing, if we're analyzing this part or if we're analyzing this part, and also think about our mitigation measures. Where are they focused? Are they focused to avoid initiation here, or are they focused to protect exposed elements in the runout zone? Because then the type of measures are going to be different. A landslide occurs whenever we have an unstable slope, and an unstable slope occurs whenever the factor of safety, which is the numerical measure of the stability of the slope, becomes lower than 1. The factor of safety can be defined simply as the relation between the resisting action and the driving actions on a slope. This is a simple example where the resisting actions are given by the shear strengths distributed, soil shear strength distributed along the potential failure surface, shown as these green arrows, and the driving actions are produced mostly by the action of the self-weight of the sliding mass. So our aim mostly is to try to have a factor of safety larger than 1, but in practical situations, the factor of safety cannot be accepted as marginally near 1. So we need in practice to have a certain margin of safety, and that varies depending on the regulations and standards for different countries and regions. For example, in Europe, typically factors of safety for some situations, the limiting factor of safety is 1.25, while for other situations can be 1.4. In Norway, on the other hand, I mean, this same convention is accepted as in the rest of Europe, but for some special circumstances, for example, for important roads or railways, then the factor of safety requirement is more strict than that. So it's not 1.4, but 1.6. A landslide can be triggered, of course, whenever the resisting actions are reduced, and also when the driving actions are increased. And here are some examples of that. After a landslide is triggered, then there's a problem that the landslide will propagate or will with having some maximum runout and having some distribution of thickness and some velocity. And the landslide intensity or hazard intensity in this case is directly related to these two properties, the thickness or depth and the velocity. This landslide propagation or runout can be quite dramatic. This is an example from Central America in 1998, where a landslide that was triggered at the top of this volcano traveled as far as 20 kilometers from the summit, and 6 kilometers away from the release area there were two settlements where nearly everyone was killed. So 2,500 people were killed this far from the initiation area. So in this case, you see, in spite of the long distance, the initiation area was relatively small, a few hundreds of meters, then the consequences were very dramatic. Landslide intensity can be understood either by coupling velocity with slide volume, looking at kinetic energy, or looking at total displacement. For example, here when we couple depth and velocity, then with higher depth and higher velocities, we have higher landslide intensities. Vulnerability, as we explained before, is characterized by these vulnerability curves, and where in the vertical axis we show the degree of damage, and on the horizontal axis we show the hazard intensity. Then the vulnerability curves can have different shapes. When we have elongated shape like this one, that means we have elements that are in general exposed elements that are more resistant. But when we have steeper curves like this one, that means that we have elements with lower resistance. When we do hazard and risk evaluations, there are some methods that do semi-qualitative or semi-quantitative evaluation, but always based on the same concepts. So risk is evaluated as the product of hazard, vulnerability, and the value of elements at risk. Furthermore, hazard can be defined as the product of susceptibility factors or conditioning factors times triggering factors. Susceptibility factors, in a qualitative way, we can think that slope is a susceptibility factor that is directly proportional. So when we have steeper slopes, that means higher susceptibility. Geology is also a susceptibility factor, and that means that the lower the resistance of geological materials, then the higher the susceptibility. So they are inversely related. And groundwater is directly related in the sense that higher moisture and water pressures correspond to higher susceptibility. And there can be other factors too. Some basic definitions, we continue. Landslide susceptibility, we can somehow relate it to factor of safety as a conditioning factor. When it comes to triggering factors, we have precipitation, earthquake, anthropic, and other factors. Precipitation, it can be qualitatively described as some rainfall conditions, for example, given by a combination of rainfall intensity and duration, where events that trigger landslides are above a certain threshold, represented by this red line. These are represented by the plus symbols, but events that do not trigger landslide are represented by the minus signs here. So the challenge for risk management, of course, is to be able to derive these curves, these threshold curves, which are very useful both for hazard evaluations and also for early warning purposes. From the rainfall-induced landslides that occur worldwide, so they are quite important. In some databases, they can be up to 80% of the total landslides. Many of them transform in debris flow, about 90% of them, and this is quite important because the debris flows have a very high mobility, so long runoff distances and also high velocity. And that can have big importance in the consequences. So this is a house that has been affected by a landslide, but you can barely see that because it's a very slow moving landslide and moving only for a short distance. So the only consequences in the house has been this crack, and therefore it's quite relatively straightforward to control and to reduce consequences. But in this case that we have mentioned before, of course, the long run out produce catastrophic consequences. In the case of earthquakes, we have an additional action which is given by the uh, earthquake shaking, and this basically is adding a driving force or a driving action in addition to the self weight. Typically, in a qualitative manner, it's possible to find out which is the maximum distance at which we can expect to observe landslides depending on the earthquake magnitude. So this is some empirical curves that have been obtained by these two authors in the past. So that enables us to figure out how far we expect landslide to occur depending on earthquake magnitude. For susceptibility and hazard assessment, there are some available tools. For example, a freeware GIS platform, ILWIS, can be used for that. And there are also some application manuals to show how to perform deterministic or statistic evaluations, and also with earthquake actions included. In susceptibility and hazard assessment, working scale is important. Also, quality of theme maps used as input data are important. Statistical methods require more reliable inventories in the study area. This is an example of some global inventories of landslide that are available. But when we are doing regional evaluations, then it becomes very important to have regional landslide inventories of landslide. Again, an illustration of landslide risk assessment. So we have to take into account the probability of initiation of a landslide, and also the probability of the landslide having a certain runout, and the probability of that landslide hitting an exposed element. And this is in the case of buildings, but the same thing we can apply also for exposed persons. And then there are a number of problematic aspects in risk assessment, as mentioned here, to figure out volume and type of landslide, the runout distance of the landslide, degree of damage to different types of elements at risk, the spatial probability of landslide initiation, temporal vulnerability of elements at risk, and so on. There are some methods that are based on a more heuristic approach, like this flowchart that describes an NGI method used in several projects done previously for the World Bank and for the United Nations International Strategy for Disaster Reduction. NGI was in charge of doing this type of evaluation at global scale, and then later, some years later, we did similar evaluations also at country scale for both Indonesia and for El Salvador. Now, after these basic concepts, we're going to get into talking about landslide flow path analysis. Yeah, we discussed already about the landslide flow path analysis, basically about trying to simulate or to model the runout behavior of a landslide. So that means how far the landslide will travel, what will be the distribution of depth or thickness, and the velocities over the runout behavior. Then the simple way to look at the runout behavior is by representing the landslide mass as a block here, this red volume, and then this is a block that is sliding down a slope, and then in the contact between the block and the terrain, then we have some normal stresses, some shear stresses, and the block is sliding at a velocity v, and then there is a width of the shear band here called ds. So the basic material properties for defining the behavior of a landslide in the runout phase is related to defining its rheology or material properties. So in a simple way, the rheology is a model that allows me to calculate how much or how large this shear stress becomes during the runout. And of course, you can imagine how this shear stress is related to the runout behavior, because the higher the shear stress in general, then the shorter the runout will be. So the variations of shear stress are basically going to control the behavior during runout. These are three very common types of rheologies. The frictional rheology, in which the shear stress is related to the normal stress and a friction coefficient. The Fermi model, which is similar to the frictional, but in addition, we have also a dependency on the velocity and on a parameter called turbulence coefficient. And finally, the Bingham model, where the dependency of the shear stress is on the two properties, the yield stress and the viscosity, and the shear strain. The shear strain is just given by the ratio between the velocity and the width of the shear band. All these terms in blue are basically material properties, so we have to figure out a way of calculating them. The Bingham rheology is quite simple to represent. This one. So here we have basically two parameters given in this curve of shear stress versus shear rate. The first parameter, the yield stress, is basically the intercept or the breaking point between this vertical line and this inclined line, and the viscosity is given by the slope of this second segment. So the behavior is given by these two red lines. These yield strengths and viscosity, they are related mostly or to volume concentration of sediments, as shown here. So this means that when we have less or a lower concentration of sediments by volume, or in other words, a more dilute landslide, then that will correspond to a lower yield stress. And as we increase the concentration of sediments by volume, our yield stress will increase. And the behavior is different for clay than for sands. A similar relation exists between dynamic viscosity and volumetric concentration. So when we reduce the concentration of sediments by volume, or we have a more dilute flow, then that also produces a reduction in the dynamic viscosity. There are some key terms for mass movements in the flow category. For example, rapid and higher and less than rapid. Normally, the type of events that are more important to model in the runout phase are those that have rapid and higher rates of movement. And there is also a classification of flow type landslides done by Hunger, which is shown in this table. When we have landslides of the flow type, like debris flow, they have different phases within the same landslide. So here we have, for example, debris flow, which has a bouldery front, then a slurry flow in the middle, and then a hard peak concentrated stream flow, or less dense flow at the tail. and we have a precursory search at the front here. So there are different types of phases even within the same landslide. The velocity classification according to Cruden and Barnes. So this category is quite important because when we have landslides occurring in this category, then there may not be enough time for evacuation, and then for this category of landslide, it becomes extremely important to have other types of measures like early warning systems. The runout is basically a component in quantitative risk assessment frameworks, like here. So we have to basically connect runout with susceptibility. And here we have the runout models that play a role in the evaluation. Then the question that have to be answered is how much material will be displaced, where will the zone of impact be, how long will it run, will it cause damage or victims, how fast will it move. There are different approaches for runout evaluation. We can have 1D approaches, 2D approaches. The 2D approaches are based on depth average continuum modeling. They are mostly all these models have to take as a basis the equations of conservation of mass, this one, and the equations of conservation of momentum. And in the equations of conservation of momentum, we have some terms that incorporate the rheological or the shear stress, which is basically controlled by the rheology. And these are other formulations for the rheologies we were mentioning before. This is another type of rheology, the quadratic, which is used by other models like Flow 2D, for example. This is an overview of runout prediction models. Currently, we are mostly concentrated in continuum-based simulation models. There are, for total travel distance, there are some approaches that are used, like these ones. There are also useful plots for preliminary evaluations of runout, where we can relate the travel angle or runout angle to the volume of the landslide. Also, we can relate travel distance to this formula that relates the volume and the run on the height. There are also approaches that evaluate runout length in the depositional zone. For these are some empirical values that have been observed for large debris flows. The deposition starts once the gradient in the channel is more than 6 to 12 degrees. For small and unconfined debris flow, the critical deposition slope may be as high as 27 or 35 degrees. In general, it is often assumed that debris flow deposition begins at slopes of 10 degrees. There are some volume balance approach models like LAHAR-Z, developed by the USGS, which is illustrated here. So the basic of the model is that one defines basically the uppermost part of the deposition fan, and then the model is run from there downstream. There are some relations also based on observations relating runout length and observed runout length. And finally, the continuum-based dynamic simulation models that are mostly used, and we have been recently using with colleagues from ADPC and NBRO in Sri Lanka, are these type of models for conservation of mass and momentum. So these are 4 examples of models, of such models we have been using in this ongoing project in Sri Lanka at the model done 3D. At NGI, well, we have experience in using all four models, RAMS, Flow2D, done 3D, and Bing. Finally, talk a bit about landslide risk mapping. Landslide risk mapping, basically, it's in practice, it's carried out by first estimating initiation or source areas, and then performing risk mapping by combining runout and loss estimates. The estimation of initiation source areas is done first by running a software for slope stability. Then we define the areas that have a factor of safety less or equal than a prescribed minimum, and those will be the areas at failure. And then these areas at failure are used for the selection of initiation or source areas to be used in a subsequent runout analysis. In this presentation, I'm referring to the software TriggerS, also developed by USGS for this estimation. This is a freeware. This is software for rainfall-induced landslides, not for earthquake-induced landslides, and it's valid for triggering rainfall of relatively short durations. The main input data for TriggerS is the terrain model, also a model with depth to the bedrock, the initial groundwater table across the domain, also the unit weight of the soil, shear strength parameters, permeability of the materials, and unsaturated properties. And finally, the triggering event is given by a rainfall event that can be distributed over the region of interest. The main result that the model provides is the spatial distribution of minimum factor of safety and the depth of the minimum factor of safety at each cell or pixel. This is one example of the tutorial data that TriggerS uses. In this case, you have a DM where you have lower elevations here, and then the slope is, or the elevation is increasing to the northwest. The slope is shallower at this bottom of this valley, but the slope becomes steeper at the middle of the slope approximately. And then these are other plots showing basically the depth to bedrock, the distribution of cohesion, of angular friction, and then of permeability and diffusivity over the domain. Then, after one runs the model, then the most important output is the distribution of factor of safety. So here we can see that the lowest factor of safety are obtained in these parts of the slope. So if we were to continue the evaluation here, then this would be the areas where we should continue running runout model. So this would be the initiation areas to be used in a runout assessment. Then finally, the risk mapping is performed by combining both runout and loss estimates. So we carry the runout analysis for volume and rheology that corresponds to the return period of interest, and this requires prior calibration of parameters, an analysis of the inventory, and a complete precipitation records. We need to calibrate vulnerability curves. We need to obtain hazard intensities for each exposed element by overlaying map of elements, footprints, and result of runout analysis. Then we need to calculate the degree of loss for each element and multiply by its cost, and divide the previous value by the return period of interest in order to estimate risk. And finally, we can map the spatial distribution of risk for all exposed elements. So this is what I had to say for this first lecture. I would like to thank you for your attention. It is really unfortunate that we don't have the possibility to exchange, to have an exchange of comments now live. But of course, please feel free to send your questions by email to me, and if possible, I think if possible to have some discussion with my colleagues who are present who are physically present in the regional meeting. Again, thank you for your attention, and I'll see you in the next lecture soon. Thank you very much.